too had a good weekend. Frustratingly, I didn't have some of my Monday was pretty bad. And that's because I went to 4 or 5 different stores looking for some components for the lab I was planning for this week. And no one was selling them. So I just don't have what I had planned for this week's lab ready yet. So that plan is just going to need to be a waylay. And I'm upset about that because it was going to be fun. We were going to build motors and it was going to be cool.
So what are we doing?
That's a good question. We need 2 more lab grades in by the end of the semester. We have this week for that. We have the last week in April for that as well. So this week I'm going to be posting, before lab period starts today, a kind of a research-based assignment where I'm looking into some specific magnetic phenomena and how motors work, just to kind of get some of the preliminary steps out of the way, because I want to build these motors. It's fun, it's very obvious when it works, and I think there's a lot of potential for what we'll be able to do there. So I want to do that lab, and we're going to do that lab. I just apparently need 3 weeks to find magnet wire and neodymium magnets, because no store in the Tri-County area has them. So that lab will probably be had the last week of April. This week, I'll be posting an online kind of research-based assignment, because I apologize for this, I just don't have any other actual laboratories prepped. On top of it being a crazy semester, magnets are tricky and hard to visualize. So this was my plan and it didn't work.
It's okay.
So I apologize for that. There'll be a different assignment that won't be too time consuming, but it'll be a little more research based. I'll be in lab room during this week, but you have no obligation to come. I'll just be there if you have questions. And in case people don't come in person to work in the room, I'll take it by the end of the week. Why don't you just send me a copy with your group's answers on it? It'll just be some short answer research type questions where you look into a specific phenomenon or how the thing works.
We're working with our group for it?
Yes, absolutely. Teamwork is always a good thing. You can do it by yourself if you want to, or you don't have to. I know a couple students are either late or won't be here today, so we'll just continue and I'll catch people up as they show up later. So, brief synopsis of what we've already talked about. Lab this week online, in-person lab last week of April. We will not have lab these next 2 weeks because next week there's no class Tuesday, and the week after that is both contains Honors Day, and that will also be the week of our next test. So, test upcoming during this week. It'll be on, most like the last one, it'll go up on a day of the week, and you can pick any point in time you want within a couple of days to take the test. So this week will just kind of be set aside for that.
The second to last week.
Correct.
Okay.
So the test will go up on the 20th, and you'll need to have it done by the 23rd.
Okay.
And then we will spend, there won't be any lab that week because Honors Day and tests, that's enough for you guys to be dealing with. Last week of April, we'll have class, we'll have lab, we'll begin talking about ending of the semester and also reviewing. I want to talk about waves because light and sound is very important for your life as a human. And then first full week of May is the last week of class. We will only actually have class on this Tuesday because Thursday is reading day and then exam starts. So this is our last day of class. We'll spend it reviewing, making sure everyone knows everything they need to know. And that means the week before that will also be mostly exam review and light waves, optics, such.
Our dinner exam is still on Mother's Day.
Great question. Technically, yes. However, most people aren't a fan of that. And given that last year I gave the exam on the website, my thought is if I put it up on the website like I gave a test, it could be open at the start of exam season and be open until the end of exam season. Because I don't really care what you do within that period of time.
Perfect.
I don't know if I'm officially allowed to do that, so this is like a, it's not really under the table, but parallel with the table.
Fair. That'll be our secret.
Their exam schedule will be bonkers, and I'm conscientiously objecting.
Do you like the new class schedule?
No.
I hate it. And you're doing physics 1. Oh my gosh, I would have not. You're doing physics 1?
Yes.
Next semester?
Yes.
Yes.
Oh my gosh.
I'm so sad about that.
I'm jealous of every single person ever.
Aw.
That.
It just,
No offense.
who has it just rotates every year or so. Like, I start with 1500 and I continue on to 1510 with a group, and then Dr. Rodekar starts with a different group and continues on.
Yeah, really?
Well, okay, no. In the past couple of years, it's been a crapshoot because
I would say that's not.
people leaving, people coming, people leaving again, Dr. Rodekar going on sabbatical, that's turned the whole thing into chaos. Besides the fact that the schedule is now bonkers, and I can't arrange it to where I have a Monday or a Friday off, so I have to take a Thursday off. The new schedule is weird, and every meeting I've had with all of my coworkers has been negative about it. They're all confused and frustrated. We don't know why they did it the way they did it. I wasn't necessarily opposed with overhauling, retooling the schedule. I just don't know why it's the one they went with.
I just don't like that it, I don't know, it probably just takes time to get used to. I don't like that it starts at 30 and ends at, what, is it 20 or something?
Yes. Yes, it does.
It just makes things more confusing.
Yes.
But that extra 30 minutes of sleep is going to be nice.
Yes, as long as your schedule arranged itself such that you start 30 minutes later instead of 30 minutes earlier.
That's true.
That said, the extra 30 minutes is very appreciated for me because next semester I will be married and living in Irmo, so I'm going to be driving every day.
It's a lot further to run that.
Oof,
How far is Irma?
50 minutes. I like driving, but the extra 30 minutes is convenient for if I don't call myself out of bed in time. Okay, a lot of scheduling talk. I'd say the most important short-term thing to remember is the current homework assignment for the kind of lump sum of chapters about magnetism. I've created one assignment that's 19 and 20 and a little bit of 21 as far as the book is concerned. That will be due next Thursday because we're going to spend this week talking about magnets and we don't meet next Tuesday.
Will we have another homework after this one?
There will be one more assignment about anything we talk about related to waves.
Okay.
But that'll be due by the end of this week so that we aren't worrying about it the next week. Because if it's not an official school rule to not have assignments the last week, it needs to be.
It's definitely not, because I have several things due to that last week.
Ooh.
You're the only understanding professor.
I don't want to chalk it up to the professors lacking empathy, because I don't know them all as However, I assume that I'm younger than most of them, so I remember, my memories of dealing with it are more recent. I was a good student, but man, oh man, did I internally monologue against all of my teachers when they made me do work I didn't want to do. Okay, homework due here, no lab next week. I'll remind us of all this stuff as we go. Largely because I forget, and I will forget if I don't say it in class every single day. My memory is a whole. All the things just fall into.
I have one quick question.
Yes,
Is lab part of our overall grade or is it 2 separate grades?
it is part of the overall grade. So this is a 4-hour class, and lab is 17% of that grade.
Yeah.
That's it, everyone's doing very well. I have a grade to catch up on, but everyone's doing very well. We left off here. Yes.
Yeah, we talked about like X's and dots.
X's and dots. Okay, we did talk about that. That was a hard segue. Any questions about anything at all before we look at back into today?
Are these notes on Workspace?
They are not, because I'm combining 3 chapters, maybe 4 chapters into one, so I still need to put 2 of those together. That will be one of the things I'm doing today. Excuse me. So they will be up soon, I apologize. Anything else? Okay. We discussed right-hand rules, the force that magnetic fields exert on charged particles, and talked at least briefly about how to draw vectors pointing out of the page, vectors pointing into the page. A little reminder over here just in case. And so, doing a little bit of math now. Let's say that we have an electron passing through a magnetic field, like the one that I've drawn to the left. The electron is traveling in positive x direction at a velocity of 30 meters per second, and the field that it is now inside of points upwards with a strength of 2 Tesla. So Tesla is magnetic field strength. Our formulas are designed to take Tesla, so 2 Tesla, that's the number we want. That field points directly upwards. First question, what is the force vector acting, or that will act on that electron?
What's the charge of the first one? Oh, this is an electron. What's the charge of an electron?
Great question. And this is a known constant, so you are allowed to ask, and I will always give you the number. You are also allowed to have it down in your notes and formula sheet, and also to Google it in case of emergency. It's just a known number.
Is it 19?
It is a 19, yes, sorry. My handwriting is atrocious. The charge of one electron is negative 1.67 times 10 to the negative 19. Velocity is 30 meters per second, and M field is 2 Tesla. I don't know why what kind of force are we looking at?
Got a negative number?
Yes.
Negative 1.002 times 10 to the negative 17.
Very good. It is a force, so it is still measured in newtons. And that is the magnitude of a force. How about its direction? What direction is the field going to exert a force in?
Like, into the
Show myself, actually. Yes, into the board. And there's two ways we can write that. The problem gave us a negative number. And because of that, if we were to use right-hand rules, which are defined for a proton, and we put what we would get for a proton, which is to say positive z-axis, then this would be positive, this is negative, so that's just going to flip it, and the answer is correct. Subsequently, since this is an electron, we could think to use left-hand rules instead. We just know going into it, it should point that way. We take the magnitude and just specify negative z-axis. Zoom tight. Both of these are valid ways of writing the answer, because the vector, like the number is really just being multiplied by the direction, so they mean exactly the same thing, it's just a question of where the negative one goes. So, negative number in the positive z is the same as a positive number in the negative z.
Okay, so z is like positive is coming out, negative is coming back.
I always assume that, but I should probably check that really quickly. I always assume that it is, though. Why wouldn't it be? Yes, it is. Okay, good. I haven't been doing it wrong all my career. Okay. Now then, looking back quickly at what happens when the particle is in a field, it begins accelerating due to this force, and as it is accelerating, it remains in the field. Looking at this and knowing that the magnetic force can act as a centripetal force, what motion pattern will form for this electron, knowing that the force is going to point into the board and its initial direction is forwards.
Can you say that again?
Sorry?
Can you say that again?
Yes. So this electron begins by moving straight forwards. So its initial velocity vector points that way. The magnetic field is going to exert a force on it this way. So it's going to be moving forwards and it's going to begin accelerating in the direction of the board. But once it changes direction, the force will also change direction. So it begins forward, it's going to accelerate toward the board, it's going to start spinning in a circle on the ZX plane. Like these two begin spinning in circles on the XY plane. And that only happens if the particle is completely submerged in the field and doesn't leave it. If you enter a field and by the time you turn around there's still field, like the field was turned on and it's just everywhere now, you would keep spinning. And this is, at least partially, why the electric generators we made last week worked. We had a big copper coil with the one wire in, one wire out. Put the magnet in, move the magnetic field around, and that caused an electric current to be created. And a voltage, measured one of those two things. Particles in a field, as long as they're entirely within the field, tend to end up spinning in either a circle or a spiral. So the electrons will literally begin spinning through the helix of the coil until they just exit one side of it and head off to wherever it is they're going.
So it doesn't matter like if it's spinning clockwise or counterclockwise?
Not really, no. Some circuits, it might. Generally speaking, it won't. Generally speaking, as long as the current is flowing and there's some voltage, positive or negative, it should work fine. All the circuits we've been building would still work the same if you somehow reverse the battery. And whether or not it goes out one side or out the other is just the same as flipping the battery around. This does have a second application though, besides just generators. Have any of you looked into or been taught much about nuclear fusion?
I've heard it,
Okay.
but no.
It is literally the polar opposite of nuclear fission. Instead of particles breaking down, you slam them together and they form into heavier atoms instead. And it is what goes on inside of the sun to allow it to continue being on fire. The particles just, the sun's particles are very hot, they slam into each other, they release energy, and that's the energy the sun irradiates into space. We are trying to replicate that on planet Earth because we're going to run out of gas and coal, and we're going to run out of radioactive material to do fission experiments, so we need some other method of creating power. So there are scientists who are basically trying to create miniature suns to power fusion cells. And we use this principle to kind of create that effect. When you heat up gas, it becomes plasma. Plasma becomes electrically charged. So normal air isn't charged, but plasma is. So when you put plasma in a magnetic field, it starts spinning. And eventually, if you make it hot enough and keep it spinning fast enough, and then slam it into other hot plasma, you can sometimes, hopefully, get some of those particles to fuse together, like what happens inside the sun.
How do they never just run out? Like if we made like a mini sun, like how would it just not run out of things to run into each other?
It would run out of things, and that's why stars die.
Oh, okay.
Eventually, stars run out of particles to fuse, and they either fizzle out quietly, or they go boom.
Well, so why are we trying to make one? That's dangerous.
Well, most real suns last millions, if not billions of years. The reason we don't have fusion-powered cars yet is we have yet to create a system that can get a fusion reaction going and keep it going long enough to actually get any energy out of it. You are right, eventually it would run out of fuel. It's just really convenient. If we could get it to work, it'd be convenient because the fuel would be hydrogen gas and the byproduct would be helium.
Would it not be too hot to put in a car though?
Probably. So odds are there'd be a fusion power plant, and you'd be, just charge up your car the electrical way. But theoretically, you could have a cell inside of something powering it directly. My brain always went to star-powered cars, basically. But you're right, you eventually run out of stuff. And that is also what happens to suns.
So is that what they were doing in Spider-Man 2?
Yes, actually. The original one with Doc Ock and
Yeah.
Toby.
Yeah.
Yep, that was it.
I have a lot of issues with how that movie ended.
I mean, yeah. There's a difference between good movie and won't emotionally wreck you as a child.
Well, like, if you just drop a sun into the water, that would really cause a lot of damage.
Filmmakers aren't scientists.
Wait, what would happen if you did that?
Well, it's possible that the energy would just be absorbed by the water and it would eventually cool off.
I feel like it would
However-
just boil out of control and make a tsunami or something.
I mean, it would kill everything living in that
I
part
might
of the
boil
water.
all of NYC alive,
Mhm.
like everyone would get steamed, like the bay erupting into steam. Worst case scenario, it might boil the water, break it down into its constituent gases, start fusing those, and just keep becoming a bigger, hotter star. I think that's the worst case scenario.
Is there like, this is probably a stupid question, but is there like water in space anywhere? Like just floating around?
Not in liquid state. Most comets are made of ice, though.
Like what would happen if it hit the sun?
Evaporate. Well, it would melt before it actually made contact with the sun's surface, and then it would just end up being fuel for more fusion reactions. Actually, this is completely off of like test material at this point, but it's fun and I like thinking about it. When you actually see a comet and you see like the tail form as it is moving through the sky, so this is the rock and this is the tail that you see, that tail forms because the comet is now within range of the sun. The comet is made of ice and dust, and so now that it's close to the sun, it's literally just melting. And this is all vapor and dust coming off of the cloud, the rock ice ball as it melts.
That's pretty cool.
And that's why the tail doesn't actually follow the comet. Like, usually when you see a comet, it's not actually moving in this direction. It's moving like in this direction, and the sun is over here causing all the debris to get blasted that way. So there's a lot of ice in space, not a lot of liquid water. There's also probably a lot of steam in space and plasma made up of water's constituent gases.
My last space-related question is, what would happen if two stars ran into each other?
If you're lucky, you get one single bigger star. If you're unlucky, you get some combination of a supernova and or a black hole. And contrary to what movies might have told you, a black hole is not a portal. It is a hungry, crushing ball of death. You don't go into a black hole and come out somewhere else. You go into a black hole, and then all of your mass is reduced to the size of a pinhead.
That's terrifying.
Yes, there's a reason we don't go to those. I like getting off topic like this. I just now need to figure out where we were and where we can go next. So, one sec while I reconnoiter myself. Oh. There's a nice soft segue to get us back into things. Sample questions. Right-hand rules. we have various particles entering various magnetic fields. What will the initial direction of the force be for all of these? WebAssign, because that'll be how the homework and the test and the exam are given. WebAssign will not only give like questions in this format where it will give you, say, one prompt and then another prompt for it, and then enter a different answer for each one. The answer choices will also be multiple pictures. So say if you were doing part A here and it asked you what direction would this be, well, what direction would the force be, there would be multiple choice options specifying every possible axis, possibly even multiple pictures to choose from showing the vector. You don't have to worry about writing it in correctly or not. There will be pre-established options to pick from. No trick questions about entering the axis label incorrectly. For right now though, just using your hands, what direction would each of these initially be pushed in?
So the first one would go up.
Yes, it would.
Come out.
It would. Good catch. Second one's an electron. So it's going to do the opposite of what this says.
So you wouldn't do anything because it's not parallel.
It's not perpendicular.
Perpendicular.
It is
It is
parallel.
parallel.
So it's not perpendicular. You physically cannot represent this with your hand, which means nothing happens. You cannot point your palm this way and your fingers that way at the same time.
D, would it go like at an angle, or would it be like straight or backwards?
D would probably eventually end up moving in a helix pattern 45 degrees that way. But initially, just the initial force vector, initially speaking, since the velocity is positive y, only the x component of the magnetic field would actually matter. Like each of those field lines, like with all vectors, we can break it down into a triangle with legs. And this leg is parallel to the motion, so it would do nothing. This is the only part of that magnetic field that would affect the particle with its initial trajectory. So the direction of the initial force would be based on this velocity, this magnetic field. So into the board, that'd be the initial force. And that's all that I'm asking from this picture. How comfortable do you guys feel with the writing rules thing?
And so I'm remembering my right and left right or not.
That's fair. You can write proton and electron on your palms and left and right on the back. I do understand how follow the L. They're both L's, one's just backwards. I see how that would be a problem. Any questions? Okay. Just look ahead real quick since I'm going to be jumping around. Let me jump here instead. We have talked about how if the particle moves completely within the magnetic field and doesn't exit it, it'll end up resembling a circle kind of an orbit shape due to the fact that the force is going to constantly change directions and point towards a center of the circle. So if the particle is completely encased, it'll look like this. But more often than not, if you have a magnetic field set up here and you fire a particle into it from the side, you're going to enter it, begin orbiting, and eventually exit it again. So this tends to be what actually happens more of the time if you're intentionally shooting something into a field from outside of it. It's still centripetal motion, it just leaves and stops after a while. So as a result, you kind of end up with a slingshot type effect, where you just get bounced back. And there is actually a formula for that. Oops. Excuse me, sorry. There is a formula for this. Some people with way too much time on their hands combined the formula we just were using with the centripetal force formula. If you recall, that's centripetal force, an object of mass moving in a circle at a radius from some center point. Someone combined those formulas together to get to this formula here. This is radius equals mass of a particle times velocity squared over its charge times the magnetic field strength. And the reason this is important is because A, this radius is the radius of the slingshot effect. It's the radius of this semicircle that is formed, which is important to know if you are doing experiments where you are firing particles into a magnetic field so that you know how it's going to arc around and where it's going to come back out. That is utilized in mass spectrometry. Did I say that right? Thank you. The impression I am under about how that works is when you are looking at a sample, putting it into a mass spec, particles from the sample are blasted off with either a laser or a particle beam. Those particles are put through a magnetic field, which causes them to all turn and then strike a sensor. But because each particle has a different mass and a different charge, they're all going to have slightly different orbital radii based on said mass and said charge. And so every different element or compound will have a different arc and will end up on a different part of the sensor, and that's how it knows what's present. Additionally, sometimes if the particle stays in the magnetic field and sometimes it doesn't just move in a circle. A helix pattern is if it's moving in a circle and forwards at the same time. This tells you the radius of the helix that forms, which I don't think is used in mass spectrometry, but is used in other fields, like vacuum tubes, for example, like in old televisions. But at the very least, mass spectrometry formula. Speaking of, you know what, I should probably write that down, so I'm going to tab away from it in a second. So let's say, and this could be inside of a mass spectrometer, we have a proton being fired into a magnetic field. Its initial velocity is 1 meter per second in the positive y. It enters a magnetic field pointing out of the page, so they are perpendicular to one another. And we know its orbital radius, the radius formed by this semicircle pattern, is 5 centimeters. So what then must be the strength of this magnetic field? We're told two numbers. We want B. What can we assume about these two?
They're constant.
They are constants because this is a proton. So mass of proton, charge of proton. I have the charge closer to the top of my head. So I'm just going to write that one down first. Proton mass is 1.6 times 10 to the negative 27 kilograms.
What did you say? It's 1.67 negative 27.
Interesting. I think I was close. Yes, it's electrons that are 9 point something times 10 to the negative 21st. Is that right? 31st. Electrons are smaller. So since we're dealing with proton, these are known constants, which means if you ask me, I will tell you, and it will be on formula sheets, and it is repeatable. So this method can actually be used to determine what the strength of a magnetic field is. You fire a known particle into it, you measure what it does, and you can determine field strength, which is convenient because it's kind of hard to measure field strength directly unless you have another magnet on hand. Yes, fast.
Can you go?
What are we looking at?
I've got 2 times 10 to the number 7.
Nice.
That's
Well, we were finding magnetic field. What is the unit for mag field? Tesla's correct.
Is there any reason why that is the name of the car then?
Sorry?
Is there any reason why that's the name of the car then?
So I think Elon Musk just chose the name because it was an electrical term that he thought sounded cool. It is also the name of a person, so he might just be impressed by Tesla's work. Because Tesla was a very important scientist within the last couple of centuries. His work rivaled Edison's. And the only reason Edison is more well remembered is because he could be bothered to leave the lab to go talk to people, whereas Thomas Edison was the quintessential type A shut-in scientist alpha nerd. So he didn't get out much.
Which one was the one that got much?
Edison got out more, which is why everyone remembers him. Tesla was very important though, because his work, there was the Tesla coil, which is its own unique phenomena. Nothing to do with magnets though. So I think we gave him this unit as a severe afterthought a couple of decades later. I don't think this actually had anything to do with his work. He did, however, create the first prototype for what could be used as wireless charging. And if Tesla had gotten out more, we could instead live in a world where your phone is passively charged by the radio signal it gets to operate, and you would never have to plug it in. So be careful who you call a shut-in and keep them, because then they will never come outside and they will never share their research with the world.
It says he named the car after the scientist.
Okay. There is kind of a modern push to try to recognize Tesla the man for more of his work. So that might be why.
Nikola?
Yes, Nikola Tesla.
Do you
Nikolai? Nikola.
Do you think chargers are just a business move? Like, could we have phones that have like infinite charge?
It's not that they don't, it's just that, well, it wouldn't be perpetual motion. It would just be that they would charge from radio waves at the same rate as they are depleted. Or I would hope at the same rate as they are depleted. It could be possible for you to like be running too many apps and drain charge faster than you would recharge it. That would be a possibility. I think, A, Tesla never went outside, so our infrastructure is not based on that technology. B, if you're broadcasting power to the entire world, and if no one's receiving it, it would just kind of be wasted.
Okay.
Which is not to say we shouldn't power the world, it's just if you send out too much, you don't get it back. Okay, slingshot, radius, mass spectrometer, Nikola Tesla. Why do I have text messages from a strange number? Be gone. Okay. We're kind of just jumping between magnetic properties today. I think there's one more magnetic principle we have time to get into and successfully conclude today. Going from looking back at this formula real quick, F equals QVB. Particles have to be moving through a magnetic field and perpendicular to it is actually for there to be a magnetic force. However, this doesn't always take the form of single particles just being fired through the air through a field. There's a couple of known phenomena where a bunch of particles can move in the same direction at the same time. What happens when a bunch of electrons are all moving together in the same direction at once? Electricity, electric current. So, you can tweak the formula just slightly to look at, instead of single particles, to look at what would happen if you exposed a wire with current running through it to a magnetic field. It's ultimately the same formula, just tweaked somewhat. Previously we had Q times V, and that has been replaced with ultimately I times L, which both tell you the same amount of information. They tell you how much charge is moving through a specific amount of space and how quickly they are doing so. Previously, we just had charge times the length divided by time. In this version, current is charge per unit time, so then we just multiply it by length and we get the same units. So it is exactly the same formula. And because it's the same formula, we still have to keep the same things perpendicular to one another. So the direction of current still needs to be perpendicular to the direction of magnetic field. Based on this picture here, if the magnetic field was pointed up and down, nothing would happen because the current would be parallel. But what's happening right now is, in this picture, there's no current. The circuit's turned off. But if you run current through a wire exposed to a magnetic field, the wire will start to get pushed out of the way. And this is one of many reasons why you keep magnets away from your electronics.
Is that like the same thing where you like can't keep your like credit card and debit card on your phone?
Oh, it's like,
If not exactly yes, at least similar yes.
it's like the hotel key cards, they say, don't put them next to your phone because they'll deactivate.
Yeah, how do you get a new debit card because I can't keep my
Oops. I don't keep my cards near my phone, but they do just live together in my wallet. And I imagine those magnetic strips can interfere with each other over time.
Mine like in like the pockets that go in the back.
Ah, yes.
Don't do it.
Oh, is it the chip that does that?
I never
Pockets?
started, but society is kind of biased towards the idea of people who have pockets. But yes, if not the same, then related to both of those things. I'm not 100% certain how that technology works, but you're very good thinking, very good thinking. At least I'm most familiar with this causing a problem in literal physical circuitry, because if you hold the magnet up to the machine while it is running, wires will get janked around. Occasionally something might pull out and short with something else. Additionally, not often with physical wires, but more with, say, memory circuits, like physical, where the memory is stored in the computer. If you hold a magnet next to that, the magnet can force the gates holding the bits to open when they aren't supposed to, and the memory just escapes and is wiped.
I think I put a magnet on TV when I was little and broke it. Like it got all like.
No, that would happen here too. I was lucky in that I put a magnet on a TV, and it was an old tube TV with a giant back part. It didn't break. It did, however, turn the pixel, like, I put the magnet right there, and it turned this corner yellow.
Yeah, that's how.
But thankfully, only when the magnet was on the TV.
Oh,
When I pulled the magnet away, it went back to normal.
You know those magnets that you throw in the air and then they come together and make that funny
The
noise?
rattlesnake.
Yeah, how does that work?
Rattlesnake magnets?
Look them
I
up.
have some, I can bring the next class.
Yeah,
I-
they're so fun.
Would be interested in that, actually.
They make this it sounds like
I think
an
rattlesnakes
amplified
are
rattlesnake.
noise.
And I don't understand how it does that.
They're called rattlesnake eggs.
I can't get sound on this projector, but that's an advertisement. Thanks. This?
Yes.
Yeah.
Okay.
Ooh.
Oh, I can't hear the. wait.
Can you turn the sound on your computer?
Yeah. Can't just make my-
Do you hear it? Here, listen to this. He has music playing in the background. distracted, kind of distracted. You hear it?
Yes.
That sound.
I don't think the sound has anything to do with magnetism. That's just the sound that the physical material makes when they collide. And it's not super obvious, but because they are round, when they collide, and sometimes at weird angles, the fields will kind of make the two slide across each other while the forces equalize, and before they kind of lock into their neutral place. And I think that sound is just physically the two objects colliding and then kind of sliding, vibrating off of each other until they reach that neutrality.
You're supposed to like throw them up in the air and like it's so strong that they'll come together in the air and that's how they make the rattlesnake sound.
That is, I mean, probably. That said, this is now more magnetic fun facts. I had 2 points. One of them is still in my head. Oh, I'm trying to find similarly powerful magnets for when we make the motors in lab, because these things are just pathetic, like metrically so, and I'm trying to get stronger ones. The ones I'm looking for are probably made of a similar material. Where's my mouse cursor? Are any of you guys on the chemistry track as opposed to the bio track?
I'm technically a chem minor.
I mean, the relationship between bio and chem majors and minors sounds about the same as math and physics majors and minors.
Yeah, you just have to take like biochemistry.
Yeah, I needed like one upper level math class for the free minor, basically. Okay, there is an element called neodymium that makes some of the best commercial grade magnets you can find at Lowe's. And it's usually sold in this kind of bright silvery form. That's the raw metal. And it's just a very powerful natural magnet. And if that's not what those things are made of, it's at least similar. It's really strong, and I've had high school students who I told not to do this throw those up into the air, and they slam into each other at high enough speeds to crack. They're very strong enough to where I can put one on either side of my hand and they will remain no problem.
Is there anything you can do to deactivate a magnet to make it not work anymore?
Yes, actually. I was going to get to that next point. I would not recommend throwing any magnet up into the air because for most permanent Earth magnets, physical impact will weaken or kill them. If they hit the ground, they will eventually die.
Why?
Because, and this goes back to the weirdness of magnets and the fact that we don't know 100% certainly why this thing just has a magnetic field. When this was made, because this is like iron clay that was forged and made to have a magnetic field. This didn't come out of the ground like this. When these were forged, it's just iron clay that was exposed to a magnetic field. It aligned all the properties and particles inside of the iron in such a way that it gives off its own field. But every time I drop these and they hit the ground, those particles get scrambled and don't always line back up the way they were before. So, best case scenario, nothing happens. Weird case scenario, sometimes the poles will swap. If you took a bar magnet that was marked north-south and dropped it hard enough, you might pick it back up and those could be reversed. Worst case scenario, every single time that happens it just gets weaker because the particles don't line back up the way they were supposed to. And eventually it's just a piece of metal with no inherent magnetic field anymore. So, don't drop your magnets.
So it's like that was just like exposed to a magnetic field, and that's like why it has one now? Can you make anything magnet?
Yes, most metals, if a strong enough magnetic field, and the field is always in like the same direction, north to south, the entire time the metal is cooling, a lot of metals can be forged to be magnetic, usually with iron. I think that's what most of these things are made out of. But the opposite is also true. You can force a metal to cool and set in a way such that it no longer has any magnetic properties when you're done, which is important in medical situations because you don't want a magnet to accidentally pull a scalpel through someone. So most surgical steel isn't magnetic anymore. Same with most of the metals used inside of the MRI machine.
I saw an episode of House one time where they put a guy in it and he had like bomb fragments in his face and it like ripped him out of his face. The
Yes.
MRI machine did.
I didn't see that episode of House. I did see one episode of NCIS where the victim was of a faith that didn't allow an autopsy, but they needed to get the bullet or some part of the murder weapon out of his body. And what the family eventually permitted them to do was slide the body into an MRI, turn it on, it just flew out.
What's the difference in that and just like having surgery? Why couldn't they just do surgery and get it out?
The difference is the fact that the writers making the show thought it would be cool. Because
I mean, it's
ultimately, no matter how accurate the writers attempt or don't attempt to make it, it's still being written by a human, and therefore it is inherently flawed and is probably not matching reality in the slightest.
So when you like replicate and put across a magnet, we're just aligning the particles in like the paper clip. Then like you rub it across the magnet and then like you can stick the paper clips to it after you remove it. You're just aligning the particles within that one paper clip by rubbing it.
Yes, I might be able to do that in here. These are weak magnets, so it won't be super effective, but I have a magnet and a paper clip. For that split second after I removed this one's particles were aligned just enough to have a teeny tiny magnetic field for 1 second.
So if you never like dropped a magnet or anything, it would never run out.
Yes, which is one of the conundrums of magnetic fields because that thing doesn't really have any energy, like it can't really do work by itself. And yet when you put it next to something, it just pulls with energy that must come from somewhere.
I don't like to think about that.
Well,
It's just as frustrating to me that we don't know.
well, okay. Magnetism, electrical force, gravity are of the list of fundamental forces that hold the universe together. So at some level, they are similar to the weak and strong nuclear interaction. So it could just be that like within atoms, that energy is always exists, and you have to do something crazy to release it. I don't know, I'm not a chemist. That's one of the things that have been plaguing physicists for 8 million years. Okay, I do enjoy all these tangents. Let me see what the official notes we should end on for today. That's great. Make sure that is in your notes. The main thing to know about this formula is that magnetic fields do exert forces on wires with current running through them, which is a problem for circuits. And that is the formula for it. It works exactly the same as the other formula, just, and I can show you how those are derived.
Is there an instance where you would want that to happen?
Maybe in the case of an electromagnet, like you're turning on a magnet because you want it to do that. I'm sure there are cases, but I don't have any on the top of my head. You see how that flows.
The MS between the Q and the V is on,
That's just velocity.
okay.
So Q times meters over seconds times Teslas. Q over S, charge over seconds, is current. And meters, we measure L in meters. So exactly the same formula. The L would represent the length of wire inside of the field. So physically measure this, not the whole thing. But same formula, does the same things. And if you reverse the direction of the current or the field, you will reverse the direction of the force as well. And this is mostly a problem. You could theoretically build a system that does this on purpose because you want it to, but this is more often than not a problem. Because like putting a magnet next to a machine will make it act up for this and other reasons. But it's primarily a problem, this can be our cliffhanger for today. It is primarily a problem because when electric current passes through a wire, that wire makes its own magnetic field. So even if you never put a magnet next to your phone, every single line of circuitry inside the phone is making its own magnetic field based on the wire itself and the amount of current running through it. We'll talk more about the math behind that later. And so each wire next to every other wire is already making a magnetic field that is affecting every other wire next to it. So it's just an endless cascade of things to be worried about.
So that's why when it's next to a magnet, it messes it up, because it's messing up the magnetic fields already existing.
It's amplifying the problem, and odds are, back up real quick, this happening can be tracked to this outside field interacting with the wire's field.
So could you not just put, like, if this kept happening, could you have a magnet next to it? Could you not just put a magnet on both sides? The same, like, strength?
You could. Most of the time, what is done is you just go ahead and shove every wire in there next to each other so there's no room to move. Like in here, no matter how much current there is, they're all bunched together. They're not going anywhere.
That's smarter than two magnets.
Sorry?
That's smarter than my two magnet theory.
I mean, I'd say it's simpler. It would accomplish the same thing. But what circuit companies and people making circuit boards will also do is, if you've ever looked at a circuit board, it is very rarely, like, there's occasionally like a physical wire coming off and going somewhere else, but more often than not, it's just little trails of metal etched onto plastic, and they are, A, immobile, because the metal is just burned on, and two, they're always spaced some distance apart, and it's a very specific distance chosen to minimize magnetic field interactions from one line to the other. Because like with gravity, the farther away you get, the weaker the field is, notice bigger car, smaller magnetic field. So a lot of people have done a lot of math for every single circuit board they have ever made to try to figure out how close can we make them such that they are far enough apart to not interfere with each other. They'll also go out of their way to track what direction current is flowing through each one of these, because the direction the current flows affects the direction the magnetic field spins around the wire. And sometimes if you line them all up the correct way, the fields are all spinning in either the same direction and they don't interact, or in opposite directions and they don't interact. Which is why you never really see wires crossing like this, because that's when the fields are perpendicular and things get weird.
Man, that would be a terrible dog.
Well, that's why there's good money in it if you've got the kind of brain to be able to do that all day. We'll continue looking at this and more on Thursday, and we'll work with you next Thursday. I know if you have any questions, the lab assignment will be up in the near future.
So the homework posted right now says April 8th, it's not due.
Correct. As of last lecture, I swapped it to the 15th.
Okay.
Thank you. I have one more question.
Okay?
So wires have their own magnetic field, when like you turn the power off or something, does it lose that and have to remake it like every time?
Yes. A wire by itself with no current emits no magnetic field if it's made of just normal copper.
Does it take time to like regain that?
Yes. There is a formula for that. I just don't know it.
Well, I don't need to know it.
But yes, it does go away when there's no current. It does come back as the current starts up from 0 to max.
How do they all come back being like the exact same every time? Like, what
As
if
long
one
as it's
made
the
it
same
still-
amount of current in the same wire, the field should be the same or approximately the same each time.
But if there's like two next to each other and one made it before the other one, would that not have any impact on the slower one?
It might, the wire that turned on first might pull the second one closer to it as opposed to the other way around. But when the two magnets get closer to each other, it doesn't really matter which one started it, they're just going to pull eventually.
Weird.
And if they're far enough apart to where it's not a problem, it wouldn't really matter which one turned on first.
Thank you.
You're welcome.
Have a good day.
You too.